Good evening. It's me again. I'm a little bit more awake this time. I got home at a nice early time this evening, 8:40. So not as bad as last night. So I may not um, be as loopy. Maybe that means I won't be as entertaining. I can still. We'll see. Maybe we'll get some other kind of kookiness going. Oh, maybe we'll have instead of a clementine eyes, maybe I'll have a banana smile. I don't know. Anyway, I guess that's the secret word for today's podcast is banana smile. That sounds weird. Anyway, let's do some physics. In case I think I don't know if it cuts it off the program I'm using to record cuts it off at half an hour, and that's why last time it was the last like 2 minutes was just a black screen. In case you didn't get what I was talking about. Here is the work for that one. You can see it. There you go. Hopefully you understand it. I explained it in the last one at the end of the video. You hear the audio. Take a screenshot of that. You'll see the work. It's a bit complicated of a problem, but make sure you understand it. All right. We're going to pick up at number 56. I'm going to try to go a little quicker this time. I was a little bit slow last time. But a minute and a half in, haven't done anyone yet, so let's see. Number 56, what is absolute zero? Absolute zero, we already discussed it in one respect, having no thermal energy at all. We talked about that in a previous chapter, I believe, before we were all quarantined. Let's see what you guys said. Number 56. Oh, Jillian, I don't have your 56. I have 57, but not 56. Let's see. Joselli said absolute zero, negative 273.15 is the lowest possible temperature to be theoretically be achieved, for which he coined the term absolute zero. Yeah, okay, that is true. I'm looking for something more on the more specific. Jillian, nope, that's the wrong one. Jason, temperature where gas would have zero volume, good, and which is called absolute zero and is now represented as zero on the Kelvin temperature scale. You have almost word for word, Jason, what I have. I have the temperature at which a gas would have zero volume represented by zero on the Kelvin scale. Very good, you found the correct answer. Let's see who else is here. Jody? Barely read yours. Let's see, where's yours? Oh, it's so fuzzy. Fixed mass of gas at constant pressure is heated. The volume increases in this volume. Something is proportional to the increase in temp. I don't know. Temperature at which a gas would have zero volume. There you go, Jody. So Lisa, Lisa, I forgot to look at yours. Lisa, you said when gas was created, then it would shrink by its volume for each degree. At gas would have zero volume. Yep, good, Lisa. You have a good answer. And hope volume of gas will descend to zero at a certain temp. Good, very good. Join the resistance. Somebody bought this for me in Disney World. 57. Look at figure 13.4 on page 345. They give you the derivations of Boyle's law, a guy named Robert Boyle, named after him, and Charles' law from the combined gas law. In one scenario, the temperature is held constant and therefore taken out of the final equation. Okay, so you're looking at, let me just stop there and look at page 13.4 and page 345. Hopefully you all have those. You're looking at this thing right here. Let me look at my camera. You're looking at this right here. This little drawing here. Okay, everybody see that? You have your book out or your book from your computer out. You see that? So you see Boyle's law and Charles' law. That's from the combined gas law, which is P1V1 over T1, pressure times volume of the first thing divided by temperature of the first one equals pressure times volume over temperature of the second one. Now, if you hold temperature constant, you get Boyle's law, which is P1V1 equals P2V2. If pressure is held constant, you get Charles' law, V1 over T1 equals V2 over T2. What the question is asking, so now that we established that, extrapolate what would happen then if volume were held constant. We had, so in one of them, we held temperature constant, the other one we held pressure constant. Extrapolate what it would be if volume were held constant, what equation would it look like. Let's see if you guys got it. Number 57. Hope says P1 over T1 equals P2 over T2. Correct. Correct. Let's see if all you guys have this. Lisa is correct. Joselli is not correct. Okay, so you have, so where you have P1V, you basically wrote, Joselli, the original equation. We're looking to take volume out. If volume is held constant, if volume was taken out, what would it be? P1 over T1 equals P2 over V2. P2 over T2. Jillian, hey, you finally have one. Number of collisions. Okay, you didn't put an equation down. I was looking for an answer of what would your equation says. What would your equation look like? That's what I was looking for. Jason, P1V1 equals P2V2. You basically wrote Boyle's law. That's not what we want. We want volume taken out of the equation. If there's no volume in it, you took temperature out of the equation. What would happen then if volume were held constant, meaning it was taken out of the equation? So it's P1 over T1 equals P2 over V2. Jody, you are very fuzzy here. Yep, you got it right. Let's see who else is left. Oh, Josh. I didn't see Josh's. Where's Josh? Oh, Jake. Jake is... Why didn't you tell Jake on the previous one? Yeah, Jake, you were right on 56. And 57, you're right as well. What about Josh? Let's see if we can find Josh somewhere. Where is Josh? Josh, where are you? I have you somewhere, Josh. I must have accidentally X'd out of Josh's. One moment, please. Oh, Silas is crying. I'm not going to get him. Let's see, where are my assignments? Run web assignments, physics. All right, Josh, where are you? Good thing I saved these. There we go. I got it, Josh. Number 57. You're right. Good. I think I have all of them. 58. From the ideal gas law, you would see that a change in temperature, so ideal gas law, now what we're dealing with, which ideal gas law is found on page 340. Well, they have the combined gas law there. Where's PV equals nRT? Do they give PV equals nRT somewhere? I don't remember. Or whatever. I'm assuming that they do. From the ideal gas law, you'd see that a change in temperature would affect the pressure. Okay, PV equals nRT. In fact, since the temperature is multiplied by other factors to get the pressure and volume, that means that the lower the temperature is, the lower the pressure would be. Knowing this, tell me, in general terms, what happened to a bag full of footballs that were inflated inside of a warm locker room? Somebody goes, inflates some footballs in a warm locker room, then brought them out into a very cold stadium, maybe during a Colts game, if Colts AFC Championship game, maybe in a few years ago. Does that mean that that quarterback definitely had those balls deflated? Or does it mean that lowering in pressure happens naturally? as a result of the ideal gas law. Let's see what you say. Josh says they would deflate. One second. Sorry about that. I just want to listen for silence for a second. We do not edit these videos. Well, other people might. I'm not going to take that time. Josh says they would deflate. I wish you would have written a little bit more than that, Josh, but okay, that's fine. Yes, over time and temperature change, the football will deflate and inflate. Okay. That was Jody. Jake, lowering the temperature would decrease the temperature of the footballs naturally. You mean decrease the pressure? You said temperature. Lowering the temperature would decrease the temperature? Yeah. You think? You mean pressure. Jason's a long answer. No, the pressure would not because temperature would make it look like the balls are deflated. In reality, they just shrunk. Some instance where a cello gets out of tune, brought into a cold room, out of its pressure case. You are right, Jason. Excellent answer with excellent anecdotal evidence as well. Jillian, no, it would happen naturally. I thought you would have given a more passionate answer there, but I know you're probably still in mourning. So, temperature would change lower, so the pressure would be lower naturally. Yep. Balls were naturally lowered in pressure. Hope. TB12 for life, Patriot Pats Nation. That answer did not age well, did it? That's a tough one. That is a tough one. TB has gone to TB. Moving on, before we all cry a bit. I mean, if they were going to get rid of him, they weren't going to re-sign him for the rest of his career. Why didn't they just keep Jimmy Garoppolo? That's what I'm saying. I wanted to keep Jimmy Garoppolo 2 years ago. But they don't ask me. They don't ask me. I don't know. I'm a Red Sox guy anyway. Let's go Red Sox. Although, what's his face? I can't even think now. I'm a Red Sox fan. I can't think of pitcher there, lefty. He just had to get elbow surgery, so Red Sox are going to stink this year too. What's his name? That's right. Jake got it. Jake knew. 59. Considering the principle of thermal expansion, what is strange about the fact that ice floats? So, considering thermal expansion, what is thermal expansion? Well, what does it talk about thermal expansion on page 347? If you were to read that, it says, when heated, all forms of matter, solid, liquids, and gases generally become less dense and expand to fill the space. When heated, they become less dense and expand. That's thermal expansion. When you heat something, it takes up more space. So, what is weird about the fact that ice floats? Well, what's weird about it is that in order for ice to float, ice must be less dense than liquid water, which means it goes against the idea of thermal expansion in that when it freezes, it expands. It's like freezing expansion. So, in something that is rare, water is very, very strange. There's a lot of ways that water is strange. But water is strange in that it is the only, well, not the only substance, but it is a very uncommon substance that its liquid form is actually the most dense. So what did I write? Something like that, yeah. Essentially, in most things, the solid form sinks. Hope wrote, objects under thermal expansion tend to not float on their own opposite substance. Yeah, you're correct, Hope. Giuseppe, what is strange is that ice is made from water, which is liquid and is not the principles of thermal expansion. You could have explained that better. I know you were dancing around it, but you didn't explain it very well. Josh says, materials usually expand when heated and shrink when cold, when solid. Water expands when it is frozen. Okay. Again, Josh, I could have been a little bit more explaining. It's not the right word. Explicating. I guess I am a little tired. I don't know. Jody, water at ordinary temps contracts and increases in density as it is cooled. That's not what it does. That's what normal things do. Water further expands upon freezing. I don't really understand your wording, Jody, because you just said as it cools, it contracts and increases in density. You said it increases in density when it's cooled, but then it expands when it's freezing. So you don't explain that very well, Jody. Jake, the ice doesn't expand as all other particles would to fill space. It simply melts. No, you're off track there. It has to do with density, Jake. Jason, your answer is ice floats because it is less dense than water, dense as D-E-N-S-E. When the water freezes into a solid, freezes has two E's, only one Z. The hydrogen bonds become much stronger, putting them in a more fixed position. Ooh, good answer, though. Spelling was off, Jason, but very good answer. Jillian, a liquid in a solid state can't float. Can't float on its liquid state except water. Okay, yep, Jillian, you're basically there. Lisa, ice would be thought to be denser than water since it's cooler, and so it would be thought to sink. Water takes longer to change volume and temperature, and it first contracts. Water is dense at 4 degrees Celsius, and ice floats. You're more complicated than you need to be, Lisa. 60. What's plasma? Plasma is what it is a state of matter of negatively charged electrons and positively charged ions. You can find that on page 348. Negatively charged electrons, positively charged ions, similar to a gas. So it's very similar to gas, except gases don't. It allows electricity to conduct. Gases don't always allow electricity to conduct. It is a good conductor of gas. 60, we have, let's see. I hope you got the answer right. The gas-like state of negatively charged electrons and charged ions. Okay. This one right now. Lisa says gas-like state. Yep, Lisa, you're right. Hope, I read yours. Jillian, if I can find yours, here it is. Gas-like state of negatively charged electrons, positively charged ions. Yep, they can allow electricity to conduct. Jason wrote, plasma is a gas-like state of negatively charged ions. Yep. Jake wrote, gas-like state of negative. Yep, same exact wording, exactly. Jody, if I can make out yours, fuzzy picture here. A fundamental state of matter, the gas-like state of negatively charged. Yep, you got it. Who's left? Who did it not say? Josh. Josh says superheated gas where atoms rip electrons off other atoms. Okay, another aspect that we talk about. Giuseppe writes plasma is a gas-like state of negatively charged electrons and positively charged ions. Yep, you have almost the same answer as everyone else. Almost as if you guys all wrote the same thing. 61. Let me look at the time here. How am I doing for time? 19 minutes. Oh no! I'm frozen again. I don't know how long it's been since it froze. That stinks. Oh well. I'm going to keep going until I come to one that you have to see for. You can just pretend this is a podcast. Okay? Pretend it's a podcast. 61. How are gas and plasma similar? How are they different? Similar. Gas and plasma, they both have no definite shape and no definite size. So what no definite shape means is that they can fill their container. Water doesn't have a definite shape, so it can take the shape of its container, but solids cannot, and no definite size, meaning it can fill its container. That's like gas. Water is not like that. Solids are not like that, but it's like gas because they both have no definite shape, no definite size. It is different, however, because the particles of plasma are more energetic, so plasma can conduct electricity where gas cannot, or can not do it very well. Oh, hey, I'm back. I don't know if it froze or not or whatever, but I'm back. All right. 62. What causes water droplets to have a spherical shape? This is another thing that's strange about water. I forgot to see what you guys had for answers. I don't really need to see. I told you. It's pretty straightforward. There's no really two ways about it. 62. What causes water droplets to have a spherical shape? If you were to look at a water droplet, it looks, obviously it has a round and then it kind of has a tail at the end. But as you are seeing the droplet, it's basically a sphere that is kind of, as it's falling, it's kind of trailing behind it. But if you were to go in zero gravity, it would be basically little spheres. Even if you see a water droplet on a table, it kind of has a rounded shape to it. 62. They have a spherical shape because of the cohesive force of surface tension. Particles exert electromagnetic forces of attraction in every direction, keeping it in a spherical shape. So the particles exert these electromagnetic forces toward one another and allows it to keep a spherical shape. They're all pulling in. And it's also the fact that it has surface tension is the reason why like little bugs can stand on the surface of the water. They're able to just kind of stand on it. Have you ever seen like a mosquito or something? Surface tension, Josh says you're correct. Gisele, viscosity of each type varies with no. Gisele, it has nothing to do with viscosity, it has to do with surface tension. Cohesive force of the surface layer. Okay, Jody, but it's called surface tension. Jake, surface tension, which is the tendency of the surface of a liquid to contract the smallest possible area. Very good. Jillian, the higher the surface tension of a liquid, the more resistant the liquid is to having its surface broken. Yep, you're correct. Lisa, surface tension, the tendency of a surface of liquid to contract smallest point. Surface particles become as small as possible, and the shape with the least surface for a given volume is a sphere. Correct. Very excellent information there, Lisa. Good job. So she's saying that it wants to take up the smallest possible. It becomes as small as possible, tightest possible space because of surface tension, and the smallest volume for a given, the least surface area for a given volume is always going to be a sphere. Jason, water droplets have surface tension, the tension of a surface film of a liquid caused by attraction of particles on the surface. Yep. All right, so we all seem like we got this one right. 63. What is the main difference between adhesive force and cohesive force? Okay, so we have adhesive and cohesive. We talked about a cohesive force in the previous problem with surface tension. And if that was things, let's see how they go together. Let me go to you guys first. Hope. Adhesive molecules cling together off of surface. Cohesive molecules cling together due to mutual attraction. You can simplify it better than that. Josh. Adhesive forces. I think that's the washing machine. Adhesive forces are electromagnetic forces that act between the particles. Cohesive forces are the tendency of a surface of a liquid to contract to the smallest possible area. Well, that's surface tension, which is a type of cohesive force. Josh, you were you were right on the right track with the word between. This is not as hard of an answer as you'd think. Think of what you think of when you think of an adhesive. What do you think of with an adhesive? Tape, glue, right? Think of what do you hear whenever you hear you want cohesion, right? You think of cohesion within, like they'll be like, we need cohesion in this team. We need cohesion in this classroom. What does it mean? It means everybody working together, everybody coming together within the group. Adhesion, adhesive. I need an adhesive. I need to stick something to something else. The difference is cohesion occurs within the same substance. It's within something. So like in the colloquial definition I just gave, cohesion would be like within a group. We are all within the same thing trying to be stuck together. Adhesive or adhesion is one thing sticking to another. If I wanted to stick this to the wall, that would be adhesion. If I wanted to, within a liquid, like within water, that surface tension is cohesion because it's within the same substance. Did anybody get it? Giuselli includes electrons, attraction, wall forces. You had a lot of, you had some differences there. You were way too complicated, though. But same, Giuselli, Jody wrote same, made up of electrons. Oh no, I did the wrong one. It's just so hard to read yours, Jody. Oh, Jody's got it. Adhesive, clinging of unlike molecules. Cohesive, clinging of like molecules. Very good, Jody. Jake, adhesive forces is a clinging of molecules of unlike substances, and cohesive forces, and he trails off. He did not finish. Your first part was right, though, Jake. Kind of lost track of what you're doing. The main difference between adhesive force and cohesive force. The cohesive force. Cohesive force between mercury molecules are greater than the adhesive forces between energy and glass. I don't know what you're talking about. Molecules. All right, Joe, I think you just found the word cohesive and adhesive somewhere and just went with it. Adhesive is stronger than cohesive. Same thing with you, Lisa. It's a lot simpler of a question than you'd think. It's just adhesive, different materials, cohesive, same. 64. How does evaporation cool down a liquid? Okay. Evaporation happens, let's see what you guys wrote actually first. Lisa, each time a particle with higher than average energy, kinetic energy, escapes from water. Good. The average kinetic energy of a remaining, very good, Lisa, of the remaining particles decrease. Decrease in kinetic energy equals decrease in temp. She just wrote it perfectly. I wrote, evaporation happens when an individual particle's kinetic energy rises to the extent that it escapes from liquid. When that particle leaves the liquid, the overall kinetic energy of the remaining particles decreases, causing it to cool down. Basically the same thing Lisa wrote. When you have all these particles moving around, when you add heat or add energy to it, the heat's just a form of energy. They're going into the individual molecules, and each one is starting to move and move and move and move, move and shake the table, move and move and move and move, and eventually, when they move enough, they go into gas form by flying off into the air. And think about it. When that happens, the overall kinetic energy of that liquid is now lower, right? Because the things aren't moving as much as that one. When you lose that one, you have lower energy, and lower energy means lower temp. Very good, Lisa. Jillian, got it. Jake, got it. Jody, you weren't specific enough. Sally, no, because it slows down the process. No, too general. Nope. Josh, some particles higher kinetic energy. Yep, you're right, Josh. Hope, condensation to the outside of a glass. No, it's just basically the overall energy decreases. Jason, process of evaporation requires heat energy. The energy is taken away from the molecule when they convert to a gas. Yeah, basically. Yeah, a little bit different wording, but you're basically right. Good. 65. In the past, when a baby had a high fever, the doctor might have suggested gently sponging off the baby with rubbing alcohol. It's like taking rubbing alcohol and rubbing it on the baby, which is a volatile liquid. Volatile liquid. First of all, you'd have to know what volatile liquid means. Okay, volatile liquid means it evaporates very quickly. Okay, that's what volatile means. Well, that's not just what it means, but volatile liquids evaporate quickly. Okay, so knowing that, let's see if anybody got the answer correct. Which number? Lisa. Weak. No, you did not get it, Lisa. Let's see. Let's go with the next one. Oh, Jillian, where's yours? Here it is. To warm the baby up. Okay, so when the baby has a fever, Jillian wants to warm the baby up. No one let Jillian babysit their children because she wants to warm a baby up with a fever. No, the point, Jillian, is to cool a baby down with a fever. You won't be babysitting Silas anytime soon. Just kidding. Lisa, I already looked at yours. Jason, because alcohol vaporizes easily, there is a substantial evaporating cooling effect. Very good, Jason. Good. So alcohol is a volatile liquid, which means it evaporates very quickly. When something evaporates, what happens is, he missed this part, but when it evaporates, it removes kinetic energy. We just talked about those particles moving around, and as they evaporate, they remove kinetic energy. So that rubbing alcohol that you put on there, as it evaporates, it removes kinetic energy as it's evaporating. It takes kinetic energy to evaporate. It takes kinetic energy out of the in this case a small baby takes kinetic energy out of the baby as it evaporates, so it brings the temperature down quickly. Good job, Jason. Hope, I guess, like oh no. Hope wrote. Cold temperature cools the skin as it evaporates. Yes, but I wanted why. Jason got it. Is Jason the only one? Jillian warm the baby up? Nope. Evaporating alcohol would bring the body temp down. Yes, Josh, but how, Josh? How? That's what we are looking. How would it happen? Giuseppe, it would slow the fluid flow and dissipates mechanical energy. Nope. Who else? Jake. I gotta find Jake's. Jake wrote, and the alcohol vaporizes quickly. There's a very noticeable cooling effect through evaporation. Yep, you're basically right, but I want a little more explanation. But yeah, side note, you do not want to actually do this. Doctors do not recommend this anymore. There are many negative side effects that can happen from this. Hopefully nobody just stopped watching just before this. There are many negative effects that can happen to it. Doctors do not recommend this. Sometimes it can bring the body temperature down too quickly. You will not have a doctor recommend this today. I'm just saying, back in the old days, that was a trick that they used to do to rapidly bring the temperature down. But they also used to put leeches on you and remove pints of blood from your body. So doctors haven't always been the smartest. They're a lot smarter nowadays. But the science behind it is that. Explain Pascal's principles in your own words. Now, these ones I'm going to have to read because they're in your own words. Jake says, any change in pressure and force at any place in a fluid at rest is passed on without becoming reduced throughout itself. Yes, you're right, but I want it in your own words. I don't know if that's Jake's own words. Giuseppe says, heart, when an object that has, I wrote a little heart there. I don't know if she just must really love Pascal's principle. You just love Pascal, don't you? When an object that has something inside and an escape exit and it's squeezed. Not necessarily. Josh, if you put pressure on one part of a closed container with fluid, it will be exerted elsewhere. Good, Josh. That's pretty much it. Jillian, any pressure applied to a fluid inside a closed system will transmit that pressure equally in all directions throughout the fluid. Yep, that's correct. I don't know if that's quite your words, but yep. Lisa, equal exchange in quotation marks. The fluid moves or changes pressure equally according to any outside change in pressure or force. Okay. Do you understand what that means? therefore your own words. That's what I'm wondering. Jason, when force is applied to a fluid, an increase of pressure is distributed equally to all parts of the fluid. Yep, you're correct. Hope, any pressure in any non-free flowing fluid, non-free flowing, yep, will transmit to the rest of the fluid equally. Good. That's a good description in your own words. Jody, I can read it. Any pressure applied to a fluid inside a closed system will equal the pressure in all directions throughout the fluid. Yep. And I think I read everybody. I can't remember. Mine read pressure exerted by fluid is applied throughout the whole fluid. And obviously, yes, that is in a closed container, like a balloon or something. If you apply pressure to a fluid, it is applied to the entire fluid. That can be liquid, it can be a gas. You can't just apply, if you have a water balloon, you can't just squeeze part of the water balloon and have the rest of the water balloon have no pressure on it. Let's see, how am I doing as far as time? 36. I'll just keep going. Why not? Maybe I can just bang the rest of this out. 67. What force causes you to feel water pressure and air pressure? Everybody's got to get this, hopefully. Josh, you're right. Jillian, you're wrong. Buoyant force is not that. It's gravity. Just very simple. What causes everything to feel. Think about what. All right, so this is what air pressure is and water pressure. Okay. Air pressure is, if you can picture, above my head right now is a column of air, right? Just a big column of air. There's air particles. They're invisible. I can't see them, but they're air particles. As I go higher, like up a mountain, that column of air, let's pretty sure it was up to here, gets shorter and shorter and shorter, right? So it's not as heavy on top of my head. Now it doesn't feel heavy right now anyway because, air is pretty light, but there's still pressure pushing down on you. If you go up to a mountain or go up in a plane, that pressure is less, and so it's less pushing on you. If you were to go down into a deep, deep, deep valley, it would be increased. Air pressure isn't huge changes unless you go way up in a plane and then your ears pop because it's a release of pressure. When you go down into water's a lot heavier, so even at the bottom of a 10-foot pool, you can feel the difference a lot more. You feel like the water pushing down on you because water's heavier. That's what it is, a column above you, how heavy it is. The deeper you go for water, that's water pressure, and it's caused, if you picture, it's caused by gravity. Why? Because air particles, even air, is being pulled down by gravity. Water is being pulled down by gravity. So, let's see. We got... Jason said atmospheric pressure, no. Hope says gravity, good job. Jody said gravity, good job. Giselle left it blank. Jake says gravity, good job. All right, it's gravity. Very simple. Makes sense. 68. In terms of buoyant force, this is tough. Buoyant force is talking about this one. Oh, I changed mine. Okay. What causes an object to float? In other words, if an object is floating, what are the details about the forces on it? I have a different question. I don't know why, but whatever. What causes an object to float? In other words, if an object is floating, what are the details about the forces on it? Let's see. Josh says a buoyant force is greater than the top force. The object will float. Yeah, basically. Jillian, no net force downward? Not exactly. Lisa, buoyant force, increase in pressure with increase in depth creates upward force. The pressure on top is less than the bottom, and the pressure on the sides is equal. There you go. That's the key right there. Simple terms. Sometimes it can be just very simple. You can be detailed, but still be simple. Pressure on top is less than the pressure on the bottom. Pressure on the sides is equal. Buoyant force is the force, Jason, that causes something to float. Yes, but I want you to explain it. Hope, buoyant force versus object weight. Okay, yeah, but explain why it floats, because it's less pressure. Jody, the force is acting back on the object are greater than the force of the object is exerting. Giselle writes, heart, buoyant force. You want buoyant force for a couple in a row here. Yes, but explain buoyant force. Jake, buoyant force is balanced with gravity. I don't know if it's balanced. Well, I guess so, yeah, because if it's just staying still, it's not moving. So yeah, we balanced. Essentially, the upward pressure of the bottom of the object is causing upward force is greater than the downward pressure, or equaled out. 69. Oh, you know what? I did have that one. I had okay. 69. Yeah, for an object that floats, what determines? I don't know. I was confused for a second. Just ignore me. 69. For an object that floats, what determines how much of it will be above the water? Okay, this is a good one. What determines how much of that object will be above the water? I want to see what you guys have here. It's really interesting. This is actually a really interesting concept. Josh says it's density comparison to the water. I mean, in comparison to the water. Jillian, I want a little more. Josh, I want a little more detail on that. Jillian, how much force is acting on the object? The weight and density of the fluid and the volume and gravitational acceleration of the object. Lisa, it's tough because you did yours in pen, so I don't know how you're going to change it. Hopefully you have whiteout. Jason, the volume of the fluid displaced is equal to the volume of the object submerged. You're very close. You're right there. Hope says Archimedes' principle. Okay, yes. Yes, but I wanted you to explain it. Jody says density. Okay, that's part of it. Joselle, buoyant force, no. Jake, the amount that floats is proportional to the amount of gravity enacted on, and he trails off. All right, this is what I wrote. A floating object will float with enough volume in the water so that the weight of water displaced, so displaced means, sorry, my eyes are tired. The weight of water displaced, so when I place this cup in water, if that much of it is in the water, then this much water, however much this is, all the way around, that much water has been displaced. So the weight of the water displaced equals the weight of the object. Hope you were talking about Archimedes' principle. That's basically just talking about volume, that a certain volume displaced is going to equal, the volume of water displaced is going to equal the volume of the water in there. Yes, that is true, that the certain volume of water displaced is going to equal the volume of the object. But, like, if I put this cup into a bucket of water and some spills over, the amount that spills over, if the bucket was completely full, is going to be equal to the volume of this mug. However, that doesn't talk about the how an object floats. It has to do with how much of when the weight of the water displaced equals the weight of the object. Okay, so like if you have a 5-pound object, a 5-pound object is going to displace, if the object is 5 pounds and its volume of water is 5 pounds worth, then it will float. Do you guys understand what I mean? A beach ball. A beach ball will float because it is this big, and this much water is way heavier than this much beach ball, right? All right, so but this is for floating objects. For floating objects, how much of it is in the water is basically equal to the volume that's in the water versus the volume of water, weight of water. 70, for an object, any object will float if its density is blank than the fluid in which it's submerged. Submerged is just less. Obviously, everyone should get that right. Everyone should get that right. Lower, less, yeah. Please, everybody get this right. Less. No, not multiplied. It's less than the fluid in which it's immersed. All right, almost everybody got that right. So it's less. 71, a cork is floating on water with 1/10 of its volume below the water. What is the density of the cork compared to the density of water? Well, if 1/10 of the cork is floating in the water, then that means the density of the cork is 1/10 the density of water. Simple as that. And if you knew the density of water is 1.000, then you'd know that, or 1.00, you know that the density of the cork is 0.100. Let's see, you've got it 1/10. Jillian, I don't know what you're talking about with your answer. Lisa, what number am I on? 71. Lisa, cork is only 1/10. Yep, correct. 1/10 of water. Jake, you actually wrote the number out. You wrote 100 kilograms per meter cubed. You need 0.100. Okay, because you thought of water as 1,000, but it's really 1.00. It's hollow and floats, Giuseppe. No, I'm looking for an actual number, so just 1/10 of water. The density of the cork is 9/10 more dense than the water. No, Jody, that's not correct. It's 1/10 of the water. Hope, no, it's not the same. It's 1/10. Jason, good job, 1/10. All right, 72. Which displaces more water? Oh, you know what? Let's do something. Let's see let me look at my 46 minutes in. I'm sorry. Let's do some entertainment. Hello, how are you? I don't know. That was me being entertained. I don't know. 72. Which displaces more? Let's just run through this. It's gonna be a long video. Let's just get through it. Which displaces more water when placed in an aquarium? A 1 kilogram block of aluminum or a 1 kilogram block of lead? Which displaces? You know what? Should I do a third video? You know what? Let's just do it now. So I mean, you can press pause and come back later. What am I talking about? Which displaces more water? 1 kilogram block of aluminum, 1 kilogram block of lead. You had to come to this knowing that lead is heavier than aluminum. Okay, so I assumed something here. I assumed that you knew lead is heavier than aluminum. Okay, so therefore, a 1 kilogram block of lead would be smaller than a 1 kilogram block of aluminum. If you didn't know that, then you probably wouldn't have been able to get this question right. But lead is heavier than aluminum. So if they're both 1 kilogram, the lead's going to be smaller, the aluminum's going to be heavier. The block of aluminum displaces more water because aluminum is lighter than lead. This means that in order to get the same weight sample, you have to have more aluminum, right? A block with a mass of 1 kilogram of aluminum would have a bigger volume, and then a 1 kilogram block of lead, so it would displace more water. If you put both underwater, then the aluminum would displace more water because it has a larger volume. B, which displaces more water. A 10 centimeter cubed, so this volume, 10 centimeter cube block of aluminum or 10 centimeter block of lead. Why? Well, both samples have the same volume this time because volume matters with water displacement. Hope Archimedes principle. B, so they would displace the same amount of water. Okay, so the first one is the aluminum would displace more water. The second one, they would displace the same. Let's see what you guys got. Lisa, you said lead for the first one. Lead is denser. Yes, it's denser, so it's smaller, so it displaces less water. B, you're correct, Lisa. Jason, they have the same mass, so they displace the same amount of water. No, I explained that aluminum displaces more. B, you're correct, though. Hope. Let me find yours. They're the same, and aluminum. Nope, you're wrong on both. A, the aluminum, because it has a larger surface area. B, they have the same surface area, so they're the same. So you really just flip your answers. Jody, your little tiny answers here. They're the same, they're the same. B's right, A is not. Jake, where are you? Jake says, last set has a higher density. Well, it said which one displaces more, Jake? You just wrote less. I said aluminum or lead. Which one displaces more? And you said less. That's not an answer. You'd say aluminum displaces more because it has a greater volume. B should be they are the same. And Josh said check yours. I did not. You circled aluminum because it's less dense. Because it has more volume. And B, you're correct, Josh. 73. State Bernoulli's principle. As the velocity of a fluid increases, the pressure exerted by that fluid. Oh, I just did it. As the velocity of the fluid increases, the pressure exerted by the fluid decreases. Okay, so that's Bernoulli's principle. You should be able to get that pretty straightforward. I'm going to move on. 74. What do closely spaced streamlines indicate? Okay, closely spaced streamlines. Let's see. Josh says greater velocity and less pressure. Good. Let's see what everybody else said. Oh, I didn't tell Jillian's last problem. Jillian, you got to fix A on 72. I just saw yours right now. 73, 74. Which requires closely spaced streamline. Objects require less energy to move through a smooth streamlined flow. No, Jillian. It just means it's greater velocity and reduced pressure. Jody. I can't read yours. Lisa, faster velocity and less pressure. Good. Jason, friends are groups of curves that are instantaneously tangent to the velocity vector of the flow. They show direction, and so you just kind of copied an answer down. You didn't understand what I was asking. You told me what streamlines are. I'm asking what do closely spaced streamlines indicate? More velocity, less pressure. Hope. The water speeds up. Yep. Okay, well, you don't know it's water. It could be air. Something, it's more velocity, yep, and therefore less pressure. Gisele, I must not have done yours for the other one, too. Objects require less energy. Nope. Not correct. Jake, what did I have for you? Greater velocity, reduced pressure. Yes. 75. What is an amorphous solid? These are very interesting. An amorphous solid is a substance with a definite shape and size, but no regular crystalline structure. Okay, so it has a definite shape and definite size. So you'd be like, oh, it's a solid, right? Which it is, but it doesn't have a crystalline structure. What that causes to happen is they don't stay in the same structure as like a I don't know, a brick would. A brick has more of a, I don't know, brick's a bad example, but what things that have crystalline structures like diamonds aren't going to change their shape naturally. Glass is an amorphous solid. True glass actually doesn't have a crystalline structure like you would expect. So what can happen is it can actually flow. So amorphous solids can flow. It's a solid. You tap on it, it's actually, but very, 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 very slowly over years' time they can flow. In the olden days when windows were made out of actual glass with nothing else in them, because nowadays we have like tempered glass and stuff, and we have different chemicals in them, but when there was actual pure glass, what would happen after years was the top of the glass was actually thin and the bottom of the glass was thicker because the glass would flow downward over years and years because of gravity. Let's move through these. 76, almost done. 76, why could candle wax be considered a solid? Let's look at your answers for this. Jake, it hardens to become an object with a definite shape and definite volume. Yeah, definite shape, definite size. That's a good indicator. Jody, solid because when it cools, it is more dense. I'm sorry, that was just Sally. Okay, I can see where you're going with that. But Jillian, because it is a solid in its natural form and liquid when used. But what does solid mean? Solid means definite shape, definite size. Josh, it does not run as a liquid at room temperature. Okay. It doesn't run, doesn't flow, I guess. Because at room temperature, it is a solid, Jody. Yes, but describe what makes it a solid at room temperature. Why could I, at room temperature, consider it a solid? Candle wax can harden. Lisa says candle wax can harden easily to a solid state at room temp. Yes, but what makes it a solid at room temp? Jason, the state of wax before heating is a solid. Yes, but what makes it? It's definite shape, definite size. It could be considered a liquid. When could it be considered a viscous liquid? Why? Why could it be considered a viscous liquid? Because it has no crystalline shape. An amorphous solid has no crystalline shape, and it flows like a liquid when it's heated, is the correct answer. 77. What would make something malleable? What is basically, this question is saying, what is the definition of malleable? Malleable, something, Jason says, can be beaten or hammered into shapes, flattened into sheets, basically. Shaped into another form, Lisa says, and flattened, but not moved back to it. So yeah, flattened is what I'm looking for, into sheets. Jody says heat and adding heat to the object. No, malleable means you're able to shape it. Shaped into thin sheets, flatten it, shape it. Josh says structure and elasticity. Okay, yeah, you looked at like what would cause something to become malleable. I'm basically just asking like, how could you tell if something's malleable? If you could flatten it and put it into sheets. Jillian said the same thing. Jake, metallic bonds it to keep atoms in place. You kind of went to the more philosophical side. Gisele, if something is made flexible without breaking, malleable is not that. Malleable, Hope says external forces applied to a solid object. Malleable just means simply it can be flattened and shaped into sheets. What could make something ductile? Ductile, let me just, instead of reading all yours, it can be pulled into thin strands of wire, like thin strands. That would be ductile. Let's see. 79. Second, only two left. One way a solid can be defined is a substance that can be bent and resist bending. You can define substances in many different ways. Describe them. Describe the characteristics. So one way is a substance that can be bent and will resist bending. Okay, so like you can't bend a liquid, right? Referring to the individual atoms of a substance, explain why this could not apply to a liquid. Okay, so why can you not bend? So we're saying you can't bend a liquid. Like you can bend a solid. Like if I was really strong, I'd just go and bend this cup. Is there anything in here I can bend? I can bend this paper. Right? I can bend the paper. Why can you bend a solid and not bend a liquid? Let's see what you guys said. Lisa says the liquid flows freely around any solid substances, does not resist. Hope says liquids can't be bent. Yes, I'm saying why can't liquids be bent? Hope. Lisa says, I already read Lisa. Gisele, apply to a liquid because it can't be bent. Yes, Gisele, I know a liquid can't be bent. I'm saying why can't a liquid be bent? Jake says the atoms are tightly compacted and cannot be bent. Okay, the only liquid that is the atoms are more tightly compacted though is water, so this wouldn't apply to some non-water liquid, and so the fact that they're tighter would not go here. Jillian says a liquid takes the shape of its container. Okay, you're on the right track. Josh says, well, let me go to Jason, actually. I have Jason here first. Jason just says, what? Okay. Josh says, liquid can be bent but will not resist it. It also does not have a defined structure. Okay. You're right on there. Okay, the defined structure is the key, because to bend something, the thing has to have a defined structure. The atoms in a liquid are farther apart than a solid other than water. I know. So the atoms, but the key is the atoms can freely flow past one another. That's the key with a liquid. You don't. Obviously, water can take any shape, but it doesn't bend, because in order to bend, you have to have something keep a shape and be a defined shape and be able to do that with that shape. The water doesn't bend because it can take any shape. It doesn't. Its atoms flow just past one another. You can't keep them in line. In order to get something to bend, you need the atoms to stay where they are, and then you're moving other atoms around, but basically you're not changing the location of atoms. So in water, they can flow past one another. These two atoms can be next to one another, and then they can be completely far apart from one another in the next second. Last one. 80. Why do engineers put small gaps called expansion joints into concrete and steel highway bridges? Well, basically what happens when stuff heats and cools, when it heats, it expands. When it cools, it contracts. Obviously, I know that doesn't. I'm saying what happens when things, because of thermal expansion. Josh says to make room for expansion during warm weather. You're right, Josh. Jason says because when the temperature changes, the concrete expands and contracts. Yep. Specifically expands during warm weather. Jake says the bridge could collapse. Okay. Why? Not a good answer. Hope the bridge would buckle and the parts would break without them. But why? Lisa, to allow for expansion of parts in the heat of summer so the materials and structures don't bend or buckle. Okay. Yep, expansion in the heat of summer. You have those two key parts. Giuselli, to make it more accessible to the public. No, that's not correct. To make it more accessible, and to make it look nice or whatever. Make it the public be able to walk on it. No, it doesn't. Expansion joints do not help the public go onto the bridge. I mean, they help the public just not die on the bridge. Jillian, to measure its length. Nope, not it. Jody says, allow movement and prevent stress if something cracks or breaks. Not exactly. It has to do with the expansion in the heat and contraction during the cold winter. All right, I am well over an hour now, an hour and 2 minutes it looks like. So thank you for sticking with me. Feel free to take it in little bits. And we will be starting chapter 14. And I'm going to hope to get you guys on Google Hangouts and do some explanations there. See ya. Goodbye. Let's see. I'm almost at one. I'll make it 1:03 exactly. So only 4 more seconds. 2, 1. Goodbye.